2D dynamics. Okay, and the basis of all this is the Newton's laws. Okay, in fact, the law which is usually used for all this is the second law, right? The second law says that F equals ma and torque equals I alpha, where a is the linear acceleration, alpha is angular acceleration, m is mass, I is inertia. What else? F and T are force and torque respectively. Okay. For the remainder of this class, we will talk about how to do these calculations. So this is a recipe which you might have learned in any dynamics class. There are 3 steps to this. One is draw free body diagram. That is, I'm just trying to show you how to write the equations of motion. So first draw a free body diagram, then invoke Newton's laws. Okay, sometimes you have to just use the linear version. Sometimes you have to use the rotational version. Sometimes you have to use both. The third step is usually you're given F, T, M, which is a property of the body, and I is also a property. Then you can solve for A alpha. Okay, so this is what we are after, which is the equations of motion. Okay, so I don't know, you might have in dynamics, they're very particular about drawing the free body diagram. I don't know if you uh, taken that class. You probably, all of you must have taken the class. They're very adamant about it. Like if you don't draw free body diagram, you cannot compute anything. And I've taught that class too, and I'm also very adamant when I teach that class. But now I'm going to show you a method called Euler-Lagrange method, which gives you compute equations of motion. Let me abbreviate it as EOM without using free body diagram. Okay, so this is nice because now you don't really need to draw free body diagram. Okay, so I think Newton and Euler, Lagrange were contemporaries, so they came up with many things together. I mean, in different, they were not, they didn't collaborate, but they came up with things independently. So here's the way to do it without using free body diagrams. Again, we'll actually use the Euler-Lagrange method because we can then use computer symbolic package to derive the equations. So I'm just going to use Euler-Lagrange to do this. Have any of you seen Euler-Lagrange equations before? No? Okay, so let's use this. So I'm going to give you a recipe on how to do this. So this is the recipe which you might have learned in undergrad, UGrad, dynamics class. Okay, so we're not going to use this recipe because we really don't have a need for this. Okay, and then we will not really use Newton's laws, but the Euler-Lagrange equations will actually give you F equals ma torque without drawing this. And this step is common because you have to simplify things. So we'll not use 1 and 2, but use a different method. So here we go. Here is a sort of an algorithm to use Euler-Lagrange equations. Okay, so here's the steps. So number 1, write down the equations. Sorry, write the equations for the position and velocity of the center of mass of objects or links with respect to world frame. Okay, so how do we do that? Well, we know the homogeneous transformation. So for center of mass, we'll use homogeneous transformation. And we've done it lots of times. So this will be for, my bad, this will be for positions. So positions comes from homogeneous transformation. How do we compute the velocity of center of mass? Well, this is we've already done here. Use Jacobian. So V equals J times Q dot. So if G is the center of mass, you take the Jacobian of G, and then you do Q dot. Homogeneous transformation, if you remember, it was if you want the position of point G in frame 0, it's going to be the homogeneous transform times G in frame 1. Okay, and then I just put frame 1, but it could be whatever frame it is too. So that's the, so we're going to use those. The second step is we compute a special quantity called the Lagrangian. It is given as T minus V. L is the Lagrangian. Okay, it's composed of T, which is going to be the kinetic energy. So formula for T would be summation half summation, assuming there are n links or n bodies, it'll be mi vi square plus I omega I square kinetic energy. Okay, and then we'll write, well, let me put what vi is the linear speed, omega I is angular speed. Okay, now I did not write, I only wrote velocity here, linear velocity. I did not write the angular speed. Turns out for a 2D motion, it's kind of straightforward to find the angular speed. If you're doing it in 3D, we can actually write a formula for omega, just like we wrote. There's a different Jacobian which connects q dot with omega. I'll skip that because we'll not really be doing that. Okay, but you can extend that formula for the Jacobian to include angular speed. Okay, and mi and ii are mass inertia. I'll not write them down. Okay, so we got T. What is V? V is the potential energy. So here's the formula for V. V equals summation I equals 1 to n mi gi. I'm going to assume that the vertical direction is the direction which gravity is acting. So then I should just write the position of center of mass of gi with respect to 0, plus sometimes you also have springs. Anything which is conservative, like a gravity force is conservative, as well as spring force. A conservative system is such that you can express it as an energy, or sometimes if you move it in the other direction, which is moving, you get the energy back, right? If you take a ball, you move it down, there's energy dissipated, but there's energy which it loses, but if you move it up, then you gain the energy. Same for the spring. You compress it, it gains energy, let it go, it loses energy, but they are reversible. So this is going to be Kpi RP0. So RP0 is the rest length and RPI is the actual length. So Gi is gravity, Kpi is spring constant, RPI, RP0 are spring length and spring length in the rest configuration. Okay, so we are very close. That's the step 2. We've computed the Lagrange, I wrote it here, L, right? We've computed this because we've now found what T and V is. Okay, the last step, we can get the equations of motion using this formula. Okay, the formula is as follows, and I'll show you how to use the formula later on. So it's d dt of dl dq dot. So q dot is, let's put qj minus dl dqj equals qj. Okay, this equation here seems very complex. It's actually same as f equals ma and tau equals I alpha when you try to write it down. That's the Euler-Lagrange equation. Okay, here qj is the degrees of freedom. So if you have a block which is moving, q will be x. If you have a pendulum, q will be theta, and so on, right? So that's how you describe the motion. And then this capital Q, J, is basically the external force. Including damping. So note that there was no damping in the equations, right? There was no damping. There was spring force, but if you have damping, then that should go as an external force. So you could have external force could be like just push it, but if you have a motor, if there's a motor force, that motor force would be Qj. Projectile motion under a quadratic drag force. So let's set up the axis. Okay, you can put the axis wherever you want. Here, I'm just going to put it in such a way that the initial position of the object is exactly at the origin of the x-axis, x0 axis, which is fixed to the Earth. Okay, when we launch the projectile, we'll assume that it's launched with a velocity v and angle of theta. And gravity. Okay, now if there was no drag force, this is a kinematics problem, right? You have been told how to do this. This is high school physics. But if there's a drag force, then you need to invoke Newton's laws to write the equations because there's a force, and the only way force comes in this is through dynamics, which is writing equations laws. So what I'll do is, well, before I actually derive the equations, so the question is derive the equations of motion. Before I derive the equations, let me just explain to you what a quadratic drag force looks like in terms of equations. Okay, so let's say that the quadratic drag force is represented as Fd, then Fd so Fd is minus a constant times velocity squared. Okay, so if you're going in horizontal direction or vertical direction, that's how you'll write it down, v square. But we want to represent drag force for a two-dimensional object, so something which is going in two-dimensional space. So Fd has to be a vector, right? So what we do is we multiply it with a unit vector in the velocity direction. So the unit vector is just something which has direction of the velocity, but it's a magnitude unity, so it doesn't really affect the magnitude. So v square is the magnitude of the drag force, and v hat is the unit vector. So along velocity. Okay, so the way you'll write the, just make some space here. So what we can do is we can write the velocity as v, or let me write it as x dot I plus y dot j, where I and j unit vectors along x and y, right? If you want to compute v square, that's nothing but the magnitude of the velocity. So you take the individual components of the velocity and then just take the sum of squares and take the square root in order to make it, well, sorry, this should be v square. Yeah. So, and then the unit vector is the velocity vector divided by the magnitude. So it's written as x dot I plus y dot j divided by x dot square plus y dot square. Okay, and then c is a constant. So this basically tells you it's a constant for that particular drag force. So we can now take this expression. So this expression seems to have been lost, so I'll highlight it. So we need to write an expression for Fd because we need that. Now that we know what c is given, v square is here, and we know what the unit vector is, we can write a formula for Fd. So I'll write it down. Minus c v square magnitude of v is minus c. So v square is x dot square plus y dot square, and then the vector v is x dot I plus y dot j divided by the magnitude. Okay, so let's just pluck components of I and components of j. That'll be useful later on. So c times square root of x dot square plus y dot square x dot I out of c, and then minus c x dot square plus y dot square y dot j. Okay, so we'll need this, so we'll save this for later, but that's the drag force. Okay, I'm not still got to Euler-Lagrange. I just wanted this so that we'll have to use this in a bit when we write the equations. Okay, so that's just Fd. Okay, now let's get to Euler-Lagrange equations. Okay, so when you write these equations, I'm going to follow this a three-step recipe which I put down, okay, which was there in the previous page. The first step is to write the equations of the velocity and positions of the center of mass. So in this case, the projectile is in the air, right? And if you want to find the positions, we also always want to write in terms of the degrees of freedom. So the degrees of freedom are movement in the x and y directions. That's here. The positions are simply x and y, and velocities are simply x dot, y dot. There's nothing much to be done. No Jacobians needed, because Jacobians are needed if you have, the degrees of freedom and the center of mass are connected through, let's say, for a single link pendulum, you had to basically write a transformation between them. So here it is not needed. So you're good for this. The second step is to write the Lagrangian, which is t minus v. Okay, so for t, we have two parts. There's half mv square and half I omega square. This is a point body, so there is no inertia. That is, the spinning has no effect. And so we only left with one part, which is half mv square. And of course, I'm assuming that the mass is m. It's gravity. So that is, I need to write that in terms of x and y. But v, we know that v, I actually wrote it down here. This is v square is actually over here, right? So v square is x dot square plus y dot square. And then v, that's capital V, is mg y, right? So the distance from the, so since gravity is in the vertical direction, y is the corresponding distance for caps v. Yeah. So we assume unit mass for what? Oh yeah, so my bad, it should be m by 2. Thanks. Okay, so L is m divided by 2 x dot square plus y dot square minus mgy. Okay, now we have done step 2, which is calculate the Lagrangian. Now let's go to writing the equations of motion. So this might be a little new to you. That is, how do you write equations from that Euler-Lagrange equation? So I'm going to write the equation first, and then I'll show you how to derive the equations from this L. Okay, so if we have L, how do we write the equations? So the equations are d dt partial L dq dot j minus dl dqj equals capital Qj. So as I said, small qj is nothing but the degrees of freedom. So qj will be x, y, and capital Qj is nothing but all the external forces on the system, right? And so there are two external forces. One will be the x direction, one will be the y direction. So external force in the x direction will be f dx, and y direction will be f dy. And f dx is the x component of the drag force, and that's the y component of the drag force. Okay, so let's start with x. So I'm going to write, so let's call that 1. So if we take qj equals x, then we write d dt. Okay, so partial derivative of L. So L is m divided by 2 x dot square plus y dot square minus mgy. So this whole thing is L. minus d dx m divided by 2 x dot square plus y dot square minus m g y equals f dx. Okay, so you might never have seen how do you take the derivative of d with respect to dx dot. You might have seen dx right here. So all you do here is just treat x dot as the variable, nothing hard to it, right? X dot, you're differentiating with respect to d dx dot, or if you think you can call x dot as vx, if you like. So, and then this will be vx, it will be vy. So you're just differentiating with respect to that. It's very simple. When you do the partial derivative, you keep the other things constant. So when you're differentiating with respect to x dot, you treat x, y dot all as constant. So the derivative of that itself will be 0. So here, when we do this, we have m divided by 2. The derivative of this term with respect to x dot will give you 2x dot, right? Just treat x dot as a number vx. And then the derivative of this one would be 0. Derivative of y with respect to x dot will be 0, because y and x dot are different variables, and you treat y dot, and x as constant. So everything else would be 0. Okay, then when you do this part, here's something interesting happening. So we have dx, and then here we have x dot, here y dot, here y. So x and x dot, y dot are all independent. So that contribution, the entire thing is 0. Okay, so we got this. Let me just write it down. The simplified expression, it looks like this. This 2 cancels with this. The m which stays. Okay, the final step is to take the time derivative of you take the time derivative of x dot. So already x dot is dx dt, right? It's the velocity. So if you take the time derivative of velocity, you get acceleration. So we have m x double dot equals f dx, and f dx, if you go back over here, f dx is essentially this part, and this will be, it's got, this is f dx, this is f dy. So we just write that down. So what we expected for any of these problems is to get an expression for x double dot, y double dot. That's the equations of motion. So x double dot is minus c divided by m x dot square plus y dot square times x dot. Okay, but that's just one part. I've computed x double dot. I need to still compute the equations in the vertical direction or in the y direction. Okay, so I'll go a little bit faster on that one now that I went slowly on this one. So let's compute the second equation. The second part, here qj is y. So I need to do d dt of dy dot. Can write Lagrangian here, m divided by 2 x dot square plus y dot square minus mgy minus d dy m divided by 2 x dot square plus y dot square minus mgy equals f dy. Okay, so when I take the derivative with respect to y dot, The only term which will stay is the one which has y dot square. And then when I take the derivative of y with the whole thing, the only thing which will stay is probably this one, right? Because it says y. Other things are independent. So here we have m divided by 2, x dot square is 0, y dot is 2y dot minus 0 minus d dy. So that's going to be 0 for this, 0 for the second one, minus mg. So that will be 1 equals f dy. And then the next thing is I need to take the complete derivative of the first term d dt. That will be m divided by 2. I did a mistake here. This should be 2. Derivative of y square with respect to y is 2y. So the derivative of, well, this 2 and this 2 cancels. I don't have to put that here. I need to get the complete derivative of time derivative of y dot. So that's the time derivative of velocity in y direction, which will be the acceleration. So y double dot minus plus mg equals f dy, which you can check, it's c x dot square plus y dot square y dot. Okay, and then finally y double dot is minus c divided by m x dot square plus y dot square times y dot minus g. Okay, so now one thing you can do is, it's always good to check equations. You know that if the motion had no drag force, zero drag force, you can get zero drag force if you put c equals 0. So you can see if you put c equals 0, this term goes to 0, and you have y double dot equals minus d. So that's the equation of something falling under gravity. And you can go back to the first equation and see if you put c 0, then x double dot is 0, which means that the motion in the horizontal direction is not going to be affected by gravity. So that's what you would expect if you have no drag. Okay, the final step, which is not part of Euler-Lagrange, but we'll do it anyway, is we want to get intuition of how this thing is going to move the projectile under drag. So what we do is we take the equations. These are two equations in x double dot y double dot and integrate them so that we can basically get the data for the motion of the projectile and then maybe do an animation which will give us intuition and see if it translates to our experience of how a projectile might move. So the summary is, so let's just go fourth one. Simulate the system. Okay, so when you simulate the system, you need to integrate the equations. And we've done this before we've done it for the car, right? For the differential drive car, we had x dot equals v cosine, y dot equals v sine. We integrate those equations using, I think we use Euler. So we can use Euler's method, which is actually not very accurate. It depends on the step size. All of them depend step size, but you can get away with a bigger step if you use what is known as the Runge-Kuttas method. It's more famously known as RK4. This one actually is a fourth order method because the error, I think, is fifth order. That is, if h is the step size, I think the error for Euler's method is like h square, and then error for Runge-Kutta is like h raised to 5, which means that you can get away with a bigger step. And then the one which we'll be using, and I'm not going to write code to do this, but I'll just use ODE. There's a function ODE in Python which will do it. This is known as the adaptive Runge-Kutta method. Okay, so this is an adaptive method. So the difference is the h being the step size is fixed. The adaptive one, h, is a variable. Okay, the one which is most famous is in MATLAB, you might have seen this ODE45. ODE45 is adaptive Runge-Kutta of order 4, and the correction is of order 5. What it does is essentially, if you want to know, it basically tries to, the bigger the step, the faster is the integration. So what it does is basically takes a step size, let's say 0.1. It tries to find the accuracy for 0.1. It tries to find the accuracy for twice of 0.1, so 0.2. And if it finds that 0.2 gives you as good accuracy as 0.1, it sticks with 0.2. But if the accuracy is not good enough, it then drops it down to 0.1. And that way, sometime it tries to march twice of the step size, and that way you can get the integration to go much faster. We'll not be writing the code. That itself is like, you could teach a course in exactly that, all the methods to do. In fact, I'm teaching a course called numerical methods, which is some of the things related to these integration methods and so on. Okay, so we'll just be good users of a function called ODEInt, which needs, well, this is basically a Python function which does integration. I think it uses the method C. It requires the function which is to be integrated, and I'll write down what that would be. It needs the initial condition. What it means is you need to start this projectile with a certain position and certain velocity that will come in initial condition. Then you need to give it the time over which you want to integrate, and then there are some additional arguments. Okay, I'll show you this function. Okay, so what's the function? This is called that ODE fun. So the ODE fun in this case is going to consist of, well, in this case, we have a second order equation for x and second order equation for y, right? X double dot, y double dot. You can only integrate first order equations. So you need to break down each second order equation into two first order equations. So what you need to give this is, if you treat the variables as x dot, let's say x, the easiest way to do it. So x dot, what's the easiest way? Let me just rewrite the, I think my code doesn't do that. So let me just, that is x, vx, y, vy, right? This is same as x dot, is same as y dot. So what you need to do is ODE fun will be x dot equals vx, vx dot is the same as x double dot, which was here. So you'll write this one. So you'll have to rewrite this as vx square plus vy square, and then x dot, so vx. And then y dot equals vy, and vy dot equals, so that would be the equation over here, vx square plus vy square, vy minus g. So all these things will be ODE fun, which will go here, and then it'll integrate. This initial condition will be the initial x0, vx0, y0, vy0. Okay. Now it turns out that if you have a quadratic drag force, you cannot integrate the equations analytically. So when you did high school physics with no drag force, you could integrate the equations. If there's drag force you cannot integrate. So you have to use a numerical method. So let's see how to do this. And then once you get x, y, you can actually make a nice animation. So here is some code. Everything is self-contained. It's actually pretty short. 70 lines is pretty short, I think. And a lot of it I actually goes to do the animation. So the animation function runs from line 15 all the way to 40. So it's just 30 lines of code. 40 is animation. So let's run this first, and then I can explain a little bit about the code. So there's a drag force in this. So what you'll see is it looks somewhat like a parabola, what you'd expect, but then it falls down sharply afterwards. Okay. If you remove the drag force completely, so let's say the drag force I put 0.5, but let's make it 0. Okay, this is a problem which you can solve by hand. You don't need numerical algebra, but this should be a parabolic trajectory. Okay, so I think I just have window till 500. It's too much speed, so it looks a straight line. But if I decrease the speed, I have to increase the speed to make it look, because the drag force, there's a huge drag force, so I have to increase this. But if I make it 10, I think it'll work better, and you can see the motion. Okay, so that looks more like a parabola, right? So that's gravity, drag force is 0. So if you add drag force, then you really need to push it at a faster speed, otherwise it doesn't work very well. Okay, so this is a way in which you can create parameters. The good thing about creating parameters using a class is that then you can pass them as function arguments instead of passing individually G, M, C, and so on. So in this case, for example, animate, I just pass parameters. Okay, the animation part is just taking the X position, which is stored in Z, and then just plotting it. Just go plot, 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 like we've done in the past. And then there's a bunch of other things which are related to plot. And you've done this, so I will not go through those details. I told you that there is a function, the ODE function, ODE fun, that is the right over here. It's projectile. It returns, let's see the return argument first. It returns dz dt. The dz dt is x dot ax, or acceleration, y dot, or vy, and then ay. Okay, I wrote it slightly differently. I split that big expression into shorter parts. So for example, I wrote v as the square root of x dot plus y dot square. I took the drag in x, y, and then I wrote it slightly differently so that it's easier to read. But it does the same thing what I wrote down by hand. Okay, and then the part is you need to assign a certain initial position velocity, that's done here. And then the final thing is call ODE int. Projectile is a function, initial arguments, time, and then there are a bunch of parameters. In this case, I specifically passed M, G, and C, but you could also pass the whole list of parameters. Okay, so that's that. Let's run it again. Okay. So this is how it will look if you actually have drag. It goes straight up, and then it falls down, almost like there was no vertical horizontal force.